Okay, so good afternoon. This afternoon's session is on IBM Z and DS8000 performance topics, and I'm Nick Clayton. I work for the IBM System Development Organization and working mostly on DS8000 and the advanced function on the mainframe storage platform. So in the session this afternoon, we're going to start off and talk a little bit about the value of low latency from an I/O perspective. Why should we care about how fast or how slow our I/O is? And also a little bit about how this is changing in the industry. So why now? Why is this the point that this technology that we'll talk about is relevant? I also like to give an example of some technology we released last year, also in this area, just to show how we're using a range of different techniques to deliver improved performance. The majority of the session then, after that, we'll talk about the new Z Hyperlink function, which was announced over the summer, talk about the hardware, connectivity, some of the performance aspects, and also how we're enabling this from a software perspective. So quite often, if we're running a production system, we'll get a call, problems raised if there is a performance issue, if the performance, the latency is too high for their environment. So high latency has an impact. We're not able to meet SLAs, transactions fail, timeout. The question is there actually a value the other way around? So we know things are bad if latency is too high. Do we get additional business benefit if we're able to push down the latency and do things faster? So can I see an actual business value by delivering faster latency than I'm doing today? Now, if you look around the industry, I think there is certainly an argument that that answer is definitely yes. If you look at the large hyperscale web providers, they have a massive focus on reducing the perceived performance of transactions of web displays, avoiding people moving on to the next shop, the next user, a search result not coming fast enough. So there's definitely an area from a user experience perspective where reducing the latency can actually increase business transactions over time and increase revenue. There's also the fact that if I can reduce the latency of a transaction, I can actually then add things to that transaction to increase the latency again, but to enrich the transaction with additional value. So additional fraud detection. If I'm doing credit card or POS processing, if I'm running ATM transactions, can I advertise something at the same time as I give you your money and persuade you to not just withdraw £100, but also take out some insurance? So, these different aspects suggest that if we can actually improve the latency of a mainframe processing environment, we can actually deliver not just happiness in the IT shop, but additional business value and hence additional revenue, additional profit to that business. Now, we have had a long history on the mainframe of focusing on methods of improving I/O performance. All the way through the processing of an I/O, trying to minimize queuing, maximize throughput, avoid different types of issues that we could see in the processing of an I/O. Recently, you'll see some of the ones in green. We've had enhancements to our PAV processing, which enables greater parallelism per volume, new hardware to improve the FICON speeds and throughputs, Things like Vicon dynamic routing, which don't directly speed things up, but actually prevent things from slowing down with congestion. So a lot of effort on improving the performance of I/O. And these items here are, a lot of them are not related to hardware and physical media. And I think if you look in a distributed environment, that's been one thing in the last few years there's been a huge focus on. It's not necessarily making the hardware faster, but making the protocols faster. NVMe, RDMA protocols on the distributed side to enable the protocol part, the path length of doing the I/O in the software in the CPU, shorter. And one of the reasons for that is spinning physical media used to be slow, so it didn't really matter. The protocol was a small percentage of the I/O response time. As we move to flash and even faster memories in the future, storage class memories, the protocol becomes a huge component of the response time. And so we have to do something to solve the protocol part of an I/O, not just access to physical media. Now, one of the things we did last year was to introduce a function we called the DB2 Castout accelerator. And I think this is a really good example of where we look to improve the protocol and the I/O processing of a function, not necessarily anything to do with hardware or the media that the data is on. So this example we have is DB2, when we're writing out data from memory, change pages, we will do a very long chain of discontiguous writes. And each of those writes previously, we had a sync point in the Vicon protocol. So we were writing, syncing, writing, syncing. And that resulted in the protocol overheads for a long chain being very large. And what we were able to do with ZHPF and this enhancement is to get rid of those sync points and to make the disk subsystem understand that this was a long chain of these types of writes and simply sync at the end of the chain. So you see here in a simplex environment where we're just writing to a set of disk, we got 70–80% performance improvement of these cast-out chains, which can help in a DB2 environment. You're able to keep your memory free. Certain error recovery events rely on cast-out processing finishing. And so, this is a big benefit from a DB2 overall performance and resilience perspective. Now, what's interesting is the majority of people in mainframe environments, certainly in Europe, are doing synchronous replication. And actually, the impact of this change in a replicated environment was even higher. I mean, you see here an example of Metromir at 10 kilometers with a 510% performance improvement. That's 5 times faster in processing these types of chains. And this is all about optimizing the protocol. We're still transferring the same data over the same connection. We're just using it, doing it more and more efficiently, and hence are able to do it faster. Now, if I look at an example DB2 transaction here, then if you actually break down the transaction time for a transaction that's doing some reads, some updates, a fairly large part of the processing time is in I/O latency. And what's interesting is the I/O latency and the issuing of the I/O also has another factor. When I issue an I/O, I will redispatch, do some other work while the I/O completes. And getting back on the CPU also takes additional time. So you've got this dispatcher latency is a significant component as well. So it's not just a matter of saying, okay, it's the time doing the I/O. There's some almost invisible processing around that, which is getting back onto the CPU to process the I/O results. And in a heavily loaded system, that can be very significant. So with Z Hyperlink, we have taken a look at the mainframe infrastructure that we have and had said, okay, what can we do to try and create a very efficient, low latency I/O protocol? And if you look at the mainframe, a key example of an operating system getting data across a connection from another type of processor is coupling facility I/O. So I can get data from a coupling facility in a very small amount of time. And we said, can we apply those concepts and techniques to storage system I/O? And so Hyperlink is aiming to give us similar order of magnitude, around about a 10x reduction compared to normal I/O, similar order of magnitude response times to coupling facility transactions, and using very similar connectivity to short distance coupling facility connections. And in doing that and enabling that for the correct types of I/O, we can improve transaction response times and improve throughput. So this is something that we realized was going to be a very significant change for people. We have people saying this is, as significant as the move from bus and tag to SCON. It's a fundamental change in how we do I/O. And there's also some significant connectivity implications, potentially data center topology implications, because the distances we support are limited. So in order to be able to talk about this and help clients plan new installations, new data center configurations, we did a statement of direction in January this year talking about what we were going to do. So you can read the statement of direction there, and that was to enable us to start those discussions. Because a lot of people in their planning have the assumption of FICON, SANs, and all the data center considerations related to that, not related to these new connections, which are point-to-point connections like the coupling facility connectivity we have. So I want to start and just take a look at today's I/O, and you can see here I'm showing both the coupling facility and how we would be doing messaging to the coupling facility and a standard FICON SAN environment. And we might get 100 to 130 microsecond response time for a read hit in a FICON environment. And there's the additional interrupt processing time and CPU dispatch time on top of that. But the raw I/O time is in that order of 100 to 130 microseconds. And in the mainframe environment, we typically get 80+% cache hits. And for writes, we are typically 100% writing into the write cache. In fact, you always write into the write cache. It's just if you're running out of write cache, we will delay until we can find space to do that. So with Z Hyperlink, we're going to provide an additional connection. This is not replacing FICON connectivity. It's an accelerator. So you would still have your FICON SAN, but you would now directly connect your processor to the DS8000s that it needs to talk to, and now any supported I/O will be able to use the Z Hyperlink connection. Doesn't mean that all types of I/O will try to use it. You need specific enablement in the software. And we can get less than 20 microseconds being our target, a very good response time on that I/O. Similar, maybe not quite as low as the coupling facility transactions. Now, the real trick with Hyperlink IO, which we've also called Synchronous IO, is the fact that it is CPU synchronous. So we do not redispatch the processor, the unit of work. We remain on the processor, get the data DMA'd back to our task, and continue processing. So just like a synchronous coupling facility request. So there's obviously there's a CPU impact of doing that, waiting on the CPU, but you're avoiding the interrupt overhead, the redispatch. So long as the response times are within bounds, this is a neutral type of game. We win some, we lose some, but we have that data much faster than if we'd done a normal I/O. I'll talk a little bit about some of the other aspects here, about how we work in mirrored environments later. But the aim, really, with the different types of I/O is to enable I/O where you get a benefit from latency. You know, a sequential, batch processing, that's not about latency, it's about throughput. So we're not aiming to do this for certain types of I/O because it doesn't make sense. But for transactional systems, certain types of logging, when we're talking about writes, there's some big benefits in getting the latency down. So from a software perspective, this is very different. You know, we're not dispatching an SRB, we're not running processing on the IOP and doing IO in the traditional manner. The exploiting software has to understand that it's going to use a Z Hyperlink IO and then take a decision of whether it's going to do this. So if we're Sync IO eligible or Hyperlink eligible, we will do that synchronous IO processing. So remain on the processor, get the data, and continue. If that doesn't happen, or we get a failure, or it doesn't happen within the allowed time, we don't fail the IO, we will simply do the IO in the normal manner. And if you think about coupling facility, sync to async, conversion of coupling facility requests, it's a similar type of approach there that we can decide which path to take based on the behavior of the environment. The other interesting thing is that if we try the synchronous IO, the disk subsystem will have received the request. And so if it was actually a cache miss, and hence we couldn't do it in time, we will have actually started the pre-stage of that data faster than we could even get to the IOP in normal operation. So we will actually have started to stage the data, and probably that subsequent FICON IO won't be a miss, it might even be a hit, or a much faster miss operation than if we hadn't done this. So, even when this doesn't work, it can actually speed up the processing by almost prefetching that IO. So the doing IO directly from the processor to the storage system without going through the traditional channel infrastructure, through FICON and a SAN and the host adapters on our DS8000 is a major change. And there are things that are done in the channel and done in the host adapter of the DS8000 that we now needed to do somewhere else. The CRC, the integrity checking, is something that we used to do on the channel. But the traditional channel is not involved in this process, and that's one of the reasons this is a Z14 unique, is we're actually making processor and server related changes to support this new I/O connection. It's not just that it's a new channel card that you see there, but we actually have assists on the processor to handle some of the CRC checking, the integrity checking instructions that we have. On the DS8000, we already had the PCIe connections that you can see here, which we use as our internal fabric. So the servers on the DS8000 are connected to the host adapters on the front end and the RAID adapters on the back end via an internal PCIe fabric. And we have PCIe switches in that infrastructure to control the data flow. And you can see here that what we've done is basically added some additional PCIe ports on those switches to use as the hyperlink connections. So we have a channel card on the Z14 server. We have a direct PCIe connection into our I/O bays on the DS8000. There is actually a small dongle, CXP transceiver that gets added to this, so you can actually plug the cable in, but it's not a separate adapter or card. It's just using one of the PCIe connections directly into our PCIe fabric. And any machine that was purchased from the end of last year onwards will have these new bays. And any prior DS8080 model can be upgraded with a new card in the bay, which will enable these connections. And I guess also a new plate with holes so that you can actually plug the connections in. So that's an MES capability for previous machines. So one of the things that is relatively complex in a mainframe environment is defining my I/O configuration. You know, HCD specialists are rare and valued people to define an I/O configuration, all my storage devices, the connectivity, etc. And what we didn't want to do was to make this more complex when we're adding this hyperlink connection. So what we have aimed to do is to make this as simple as possible. The physical connectivity is something you have to obviously provide. It's point-to-point connections. But all we have to do is define the hyperlink and the LPARs that are going to use it. And it will automatically discover, based on the FICON connectivity, which devices it is able to be used for. So you don't have to define anything linking a hyperlink connection to a set of SSIDs, LCUs. It's automatically discovered. So it won't make things any more complex than they are today. You simply define the connection and it's auto-discovered. So from a physical connection, we have this 150 meter cable, which is the same as a short distance coupling facility connection. What's interesting is don't buy 150 meter cables if you only need a 40 meter cable. There is a noticeable performance difference from an extra 110 meters of cable. We sometimes joke that if you could get a 1 meter cable, we'll actually have the I/O done before you ask for it. But you can see the difference in different cable lengths. So optimizing those physical distances in the data center and then optimizing the cable length for what the actual distance is will actually make a noticeable difference. So we have on the server side we can have up to 32 ports, and that's 16 cards with 2 ports per card. On the storage side, physically there are up to 16 Hyperlink ports, and there's 2 of those on each of 8 I/O bays. Depending on the DS8000 configuration in terms of the number of CPUs it has, you will be able to use potentially only a subset of those ports, because we need to dedicate CPU threads to each of these connections. And if I've only got 8 CPUs and I can't use 16 ports, there would be too many threads dedicated to the Hyperlink IO. So there's depending on if you're 48, 24, 16 core, you would be able to support a different number of connections. And we say it requires 2 or more links per KEC. To be honest, in most environments, you will have 2 links per KEC. And we think those numbers, given typical numbers of storage systems involved in a Sysplex environment, will be enough for the vast majority of people. We're seeing people consolidating storage systems down significantly, and I don't think there's many people have more than 8 Z14 KECs in a single Sysplex and accessing a single disk subsystem. Now, the initial delivery of Z Hyperlink will only support reads. We have this staged software enablement rollout, but just want to explain how things work from a write perspective, because as we talk through these charts, you'll see there's some implications on your data center topologies in relation to writes, which you might want to think about. So for the reads, we're reading from the nodes on the storage system to the host. For the writes, we can't afford the overhead of processing and mirroring writes within the storage system, because that would blow our budget. So for a Hyperlink write, we actually write twice into the 2 memory locations. So it's a parallel write twice down the Hyperlink channel, stored immediately in the memory of both of the nodes that are storing the memory, and then we respond. And that lets us keep that budget down in that less than 20 microseconds. So, there's a lot of differences here, both on the server side and the storage side, how we actually process writes. Now, something we introduced a few years ago was the Z Hyperwrite capability for synchronous mirrored environments, where certain types of log I/O actually would, rather than writing to a PPRC primary, sending data to the secondary, responding to the primary and then the host, we would actually write in parallel to the primary and secondary, which means rather than adding response time, it's the longest response time of writing to the primary or the secondary. And that's very useful for Hyperwrite, because you cannot do Hyperwrite, or for Hyperlink, because I can't do a Hyperlink write and do PPRC, because I need to complete in 20 microseconds, and there's no way that PPRC processing can complete in that time. So now, if both my primary and secondary MetroMirror systems are within 150 meters, I can do Hyperwrite over Hyperlink. And that means I can complete a mirrored write, a synchronously mirrored write, in less than 20 microseconds. Obviously, that won't work if I'm doing cross-site MetroMirror. Even if it's 1 kilometer, that's too long. And I think an interesting longer-term decision for a lot of people might be, if I'm doing synchronous replication at 20, 40 kilometers, it used to be that there was a 10, 20% overhead for that distance, maybe. Now, it's 10x overhead for that distance. So will that drive people who are interested in this throughput and performance improvement to actually doing synchronous replication for high availability in the data center and asynchronous replication for the disaster recovery with either a 3-site or a 4-site solution? Now, it's not going to happen immediately. You know, this software is going to roll out. People will be evaluating how much benefit they get from it. But I do think it has the potential to change that data center topology that has become very common in Europe. What's interesting, if you go to America, if you go to China, a lot of people already have that within data center synchronous mirroring and long distance DR. But certainly in Germany, you know, Switzerland, Scandinavia, and in the UK, there's a lot of people with short distance metro synchronous environments. So, you know, it's an implication of the technology, and I think as we start to really see the benefits, people will be taking a decision based on that. So, this chart is just showing that if I have that local primary and remote secondary, that I will be using PPRC and not using the hyperlink connections for the writes. And also if I have a hyperswap and I swap to my secondary storage system, I will now start using Filecoin IO for all of the IO. Because if I move to the secondary storage system and it's at 20 kilometers, there is no hyperlink connection for that. And if I have a cross-site parallel sysplex, a multi-site workload in GDPS terms, there will always be systems that are local and systems that are remote. So there will become some asymmetry to a multi-site environment where if this mainframe is local to this and I have another mainframe here local to this, now depending on which LPAR my workload is running, it will either have local hyperlink connection or not. And again, you know, some considerations there from having a roughly symmetrical performance environment for a multi-site workload to now having a significant asymmetry, which again might drive people to local HA and remote DR. So we'll talk a little bit now about different aspects of performance, and this is a spider chart just showing how we've improved different types of I/O over time with different models of storage system. And I think what's interesting is if you look here, the actual read hit, write hit response time has only ever seen modest improvements. You know, we have had massive increases in IOPS per channel, bandwidth, IOPS on the SAP, but you know, very limited improvement, you know, 10%, 15% per generation improvement in the response time. This is giving us that order of magnitude, that leap in performance in terms of individual I/O latency. Now, we do have some preliminary results here from testing, and this is showing an example of multi-stream read IOs and the response time for Hyperlink IO and for the latest ZHPF Filecoin channels. And you can see here there is a very significant difference. Obviously, from a hyperlink perspective, the data transfer time is significant, so you can see a noticeable increase in the response time as we do more and more IOs or larger and larger IOs over the hyperlink. The thing we needn't or shouldn't forget is that that's just the IO response time. The interrupt handling, the dispatch overheads, and everything else can add up to about 700 microseconds on a heavily loaded system. So if you're running your CPU at 80–90% utilization, you're seeing additional overheads in the I/O till it gets to the application that you don't see in the RMF figures purely for the device. And that doesn't exist for the Hyperlink IO, which means that the multiplier in terms of the performance improvement is greater than you might imagine. And this example is just showing an RMF report. And I think over the years we've been adding zeros after the decimal point to the RMF reports. And I think here you can see we really need to take advantage of that. I think a few years ago it would have just shown 0 as a response time. So 15 microseconds and about 49,000 IOPS there for a single device, which is not something you could do with ZHPF without many streams of I/O. And this is at 70 meters. It'll be less than that if you dropped it down to 40, 30. Can you get a 1 meter cable? Now, this is just trying to show you what the difference could be with different types of I/O. Because obviously, for the reads, this is only affecting cache hit. And a production workload never gets 100% cache hit, which is obviously where the greatest benefit would be. So showing 90% and 80% and hybrid or all flash systems. And you can see that even with the lower hit ratios, there are some benefits, but if you're at 90+% hit ratio, using Hyperlink is really where you're getting very noticeable benefits. If for whatever reason your workload has a very low cache hit ratio, the benefits will be less. This is not a magic technology. It's dependent on us having the data in cache for the read improvements. So I mentioned that we have to enable this function in the software. So the software has to be enhanced to support using the Hyperlink technology. And as usual, we don't want to just have that automatically switched on when you enable the PTFs. So from a DB2 perspective, we have an ability to specify in the ZPalms the scope of the Hyperlink enablement. And you can see here we can enable, disable it, and we also have an option to specify database or log. Although, as I said, in the initial release, we're only supporting the reads. So we've got the support here in the software. When we get the rest of the support, we can enable the writes as well. So we are delivering this in an incremental fashion. It would have been very nice to get everything out immediately at GA time. Reality says that it's a very large matrix here of things we need to cover, and so we're delivering this gradually, enable people to start using it, testing it, and then expand their usage over time, rather than leaving it and delivering more stuff later. So at GA, we will have the DB2 read support, and obviously any transactions that are using DB2 as the back end will benefit. And from a DS8000 perspective, we will only have, at the end next month, a limited set of configurations that we will support. It will be 16 core processors, 256, 512 gigabytes of cache, and only 4 Hyperlink connections. We recognize that's really letting you test this, start to use the function, get familiar with it. In the first half of next year, we'll increase that to support all the other DS8000 models. So different numbers of cores, and the additional memory sizes. And as I said, the number of cores will determine the number of links. So if you've got the 16 core, be 8 links, 24 core, 12 links, 48 core, 16 links. We will actually be shipping an MES of the 8884 to provide more cores, which will be compulsory if you're going to use Hyperlink, because the current 6-core processors don't have enough threads to dedicate the threads to the Hyperlink. We also made statements of direction. Barbara talked earlier today about the VSam read support, so enabling Synchronous IO for VSam reads. And when we get the write support, the first exploiter of writes will be the DB2 log. Now, Hyperlink is somewhat similar to Hyperwrite from a write perspective. We cannot generically do all writes using hyperlinks, because in order to get the response time, it needs to be a well understood I/O pattern. We have to prepare to receive the data before the I/O is issued. And so, logs, anything that has a predictable I/O pattern like a log, is something we can support, but it's not going to be generic, random write type I/O, because that won't fit the Hyperwrite paradigm, the Hyperlink paradigm. So, I think what you're really going to see is the types of I/O that we can have with Hyperwrite will also be suitable for hyperlinks. So, we said that we have a statement of direction for the VSam exploitation of hyperlinks, and I've got a few charts here just going into that in some more detail and providing you some more sample performance information. So, from a VSam perspective, we're going to do the enablement disablement at an LPAR level. So we'll have an ability to enable or disable the hyperlink capability, and any type of VSam that is running on that LPAR for the reads will be able to then use Z Hyperlink. There's a IGD SMS member and a new parameter on that to give us the enablement disablement support, and you can basically set that to yes or no. Now, for DB2, we talked about the synchronous I/O that we have in a DB2 transaction, and we also in the future will get the log I/O. For VSam, one of the scenarios we've been looking at as a benefit of the Hyperlink I/O is VSam verify. So if we have a situation where a VSam dataset is abnormally closed, we have to run a verify to determine if there was a problem due to that abnormal close, set the high RBA to the correct value, and then we can reopen the data set and continue processing. So that's a critical recovery time if we have an LPAR outage, an abnormal close of the data set before you can start running again. So shrinking that time can reduce my outage time and recovery time when I'm restarting an application using a VSam dataset. And in the example that we had, we were able to reduce that time by 2/3. So significantly improving, reducing the recovery time of restarting that VSam application and the verify time. Certainly other examples, and really this is just showing you this difference. And that's not an individual I/O latency, this is a throughput example. So it's not not 10x because it's a throughput-oriented metric, but certainly a 2/3 reduction in the time is very significant. Okay, so I'm at the end of the charts here. Perhaps now, for the people in the room, pause briefly for any questions about any of the things we've covered in this session. Okay, well, thank you very much for your time, and for anyone watching over the streaming link or later, thanks for listening, and hope you've enjoyed it.